All right, today we're going to tackle a really fundamental question. How in the world do you count something you can't even see? This challenge, it's right at the heart of all modern chemistry. And the solution scientists came up with is, well, it's absolutely brilliant. Okay, let's dive in.
So yeah, this is the core of it, right? I want you to imagine trying to count every single grain of sand on a huge beach while you're blindfolded. It just sounds impossible. And honestly, for centuries it pretty much was. But human curiosity, it's a powerful thing, and it led to one of the most elegant solutions in all of science.
So, let's start with just the sheer scale of the problem. We live in this big, macroscopic world, the one we can see and touch and interact with. But all of it, and I mean everything, is built on this microscopic foundation that is almost impossibly small and just mind-bogglingly huge in number. Every single object, every living thing, even the air you are breathing right now, it's all just made of atoms. These particles are so incredibly tiny, and there are so many of them in even a single drop of water, that counting them one by one it's just completely off the table. So where do we even begin? Well, we start by looking for clues.
So the first step towards solving our puzzle, it wasn't about trying to see the atoms themselves. It was about understanding their fundamental properties. What can we actually know about them, even if we can't look at them directly?
And what's so fascinating is that even though these atoms are ridiculously small, they have these distinct, measurable properties. We can figure out their size, we can determine their mass, and, hey, thanks to chemists like Berzelius, we even have a symbolic language, a kind of shorthand to identify each one. These are our first, real, concrete clues.
Okay, so we know atoms have properties. The next huge breakthrough came from just observing that when these atoms combine to form, everything around us, they don't do it randomly. Not at all. They follow strict, unbreakable rules.
And this lays out the two big ones perfectly. On one hand, you've got the law of conservation of matter. It's pretty straightforward. You can't make something from nothing, and you can't make something just vanish. The total weight you start with is what you end with. But the real game changer for a counting problem, that's the law of constant proportions. It tells us that a specific compound has a fixed recipe by weight, every single time.
Let's make this real for a second. It doesn't matter where you get a sample of pure water, from a glacier, a river, or a lab, the proportion by weight of hydrogen to oxygen will always be 1:8. This fixed ratio is a massive clue. It strongly suggests there's some kind of predictable, mathematical relationship between the number of atoms and how much they weigh. So we've got clues about the atoms themselves, and we know they follow these strict rules of combination. With all this, chemists came up with this incredibly ingenious solution to count the uncountable. It's a concept so fundamental, it's kind of like a secret handshake for scientists. All right, let's put the pieces together. We can't see them, that's a given, but we can weigh big groups of them, and we know they combine in fixed weight ratios. So how does that let us count them? The answer is by creating a completely new unit, a whole new way of thinking about quantity. And here it is, the mole. Now get this, a mole isn't a measure of weight or volume, it's a measure of quantity. It simply means a specific number of things. And it's this ingenious bridge that connects the invisible world of single atoms to the world of grams that we can actually measure on a lab scale. Honestly, this is the absolute best way to wrap your head around it. If I tell you I have a dozen eggs, you know I have 12. You don't ask, how much does that dozen weigh? You just know the quantity. The mole works exactly the same way for chemists. It's just, well, the number it represents is a little bit bigger than 12.
So, if a dozen is 12 and a baker's dozen is 13, what on earth is a chemist's dozen? How many particles are actually in one mole?
Just look at that number, 6.022 times 10 to the 23rd power. That is a number so ridiculously huge, it's almost impossible to really comprehend. If you had a mole of pennies, you could give every single person on Earth more than $80 trillion. This is the magic number that unlocks pretty much all of modern chemistry.
This giant number has a name. It's Avogadro's number. And 1 mole of carbon, 1 mole of oxygen, 1 mole of water, they all contain exactly this many particles. Now here's the really clever part. This number wasn't picked at random. It's specifically defined as the number of atoms in exactly 12 grams of carbon-12. This creates this perfect link. The mass of a single atom in its special units becomes the mass of 1 mole of those atoms in grams. It's literally the key that lets us use a simple scale to count atoms. It's amazing.
Okay, so we've got this incredible tool, the mole, to count how many atoms are in a reaction.
But this naturally leads to another question. We know water is H2O, but why isn't it H3O? Why do atoms combine in these specific, predictable ways? And figuring out that why, well, that brings us to the final, crucial piece of the puzzle.
Really, it all boils down to one thing: stability. You can kind of think of atoms as being a bit incomplete unless they feel stable. And for most of them, stable means having a full outer shell of electrons. So to get to that happy, stable state, they'll give away or take or share electrons with other atoms. And this incredible drive to connect is what we call valency.
So, when you get right down to it, valency is just the measure of an atom's combining power. Take a sodium atom, for instance. It has one lonely electron in its outer shell that it's just dying to get rid of, so its valency is 1. Then you have chlorine, which is missing just one electron to have a full shell, so its combining power is also 1. They're a perfect match. They combine 1-to-1 to form sodium chloride. Yep, table salt. That's valency, right there in action.
All right, let's just take a step back and look at the journey we've been on. We started with what seemed like an impossible problem. How do you count something you literally cannot see? We found clues in their basic properties and the unshakable laws they follow. We discovered the brilliant solution in the chemist doesn't, the mole. And finally, we understood the fundamental why behind it all, the driving force of valency.
You see, understanding these principles is what lets us do incredible things, like design new medicines, create brand new materials, and truly understand the world around us. So the final question isn't just for chemists, it's for all of us. Now that you understand the basic recipe book of the universe, what will you build?